Good morning and Jai Hind everyone. I neeraj Sharma, Assistant Professor EC Department at Ajay Kumar Garg Engineering College, Ghaziabad. I am before you to present the lecture series for the complex topics for the subject Microwave and Radar Engineering, whose code is KEC 074. Okay, so in this lecture, I will discuss regarding the radar. Okay, so radar that is a very common thing that is right now used in the many applications, like we are using in the defense system, and also we are using it into the airports or some other different applications we are using now. So in this specific radar, okay, I will discuss regarding this radar range equation. That is very important topic that we have to cover for the some futuristics problems, and it is not just because of our aspect like that we are using for the examination point of view, but for general point of view this is having very important role. Because what is it, this radar range, what do you mean, what we will understand by this radar range, and also what are the factors that will affect the radar range, so how we can control all these. So I will discuss all the issues in this lecture. Okay, so now I am starting with this radar range equation. So here just I have mentioned here that the radar, it is simply named as radar detection and ranging. So that means what is going on here. So it is simply named as a combination of this radar detection and ranging. We are simply in a abbreviated form, we are name it as a radar. So that means what we are doing with the help of this device, what we are doing, we are able to find out the target which is at the some distance from the transmitter station, and we will want to get some advanced information from that device. So for that point of view, we are using this radar detection. That means it is detecting the target. It means where the target is now available right now, and also we want to check its shape and size also. That means at the first of all, that how much distance is far away from the transmitter. So we can also derive this range for any specific target. By in this we can detect for the radar that we will discuss in this lecture. So here this is the radar detection and ranging. So for that point of view, just I am starting with the next, that is the radar range equation. This one is very important factor, important topic for this subject, okay, that I have already mentioned. So if let's say if we are having any isotropic source like this one, and it is now transmitting like this, okay, at some few distance, let's say some is target is available, and it is simply in a transmitting antenna. Transmitting antenna from this, the distance is r, okay, that we are using. Let's say just a minute. Its distance will be r from this transmitting antenna, and the target is situated at the r distance from this transmitting antenna. So this radar range equation relates the range of a radar to the characteristics of the transmitter and receiver antenna, means this one, what antenna we are using at the transmitting end as well as at the receiving end, okay, and also the target, that means this one, about which we want to get some information, and the environment, that means the media. So this will be the general thing that I have discussed. Now we will start. So let's say we will consider that this radar range, okay, this system where it is available, that we are using the free space media. So that free space medium that we are now using here, Okay, so free space means what? That there are no obstacles between the radar antenna and the target. Means from here, this place to this place, there is no obstacle that we are, let's say, considering. And the EM waves having, for that point of view, we are using the EM waves as a transmit from the transmitting antenna. Okay, so this EM wave have the characteristic that because of this will have the sigma with itself, conductivity, permeability, permittivity, all the factors it will contains in the EM wave. So on the basis of the study of these content, we are able to detect the target. So we are using this free space medium. Okay, so what will happen in this? So when this we have considered now, after that, actually generally I will say, so just let me explain one thing in initially, that when the signal is transmitted from this transmitting antenna, from this one, let's say here we are just simply considering an isotropic source right now. As in picture you can see, isotropic source or isotropic antenna means what? It will transmit the equal power in the all the directions. Okay, so when the power is now transmitted, after that, after a certain interval, it will radiate into the free space, and after that, some of this power from this EM waves will now absorbed by some obstacle. Maybe let's say it will be available some few distance. Okay, then it will absorb some power, and the some power will be reflected back from this target to the all direction, and after that it is re-radiated back towards the antenna side. So at the receiver end, the receiving antenna having a capability to detect these reflected waves or the received signals. So from that wave, he will it is able to find out that there is information regarding any object which is available at a few distance, at some distance from the transmitting antenna. Okay, so this is simply a concept of to study the intercepted power of a target at a receiver station. This is simply a basic principle regarding this radar. So now to detect this, how much distance, after that now our interest is in that area, that at how much distance this power is this object is now available. So for that point of view, we will go for this radar range equation, where we will able to get the value of this R, and how this R, this range distance R, is dependent onto the different factors of any antenna sections. Okay, so for that point of view, just we have, let's say, transmitted a radar will transmit a power PT, means a radar transmitter transmits a power which is denoted by this factor PT. Let's say this power is now transmitted, and then the power density. So some power will be radiated by antenna. Either we are using for any different application, but specifically we are now considering for this radar. So for that point of view, we will able to understand the because we want to make the relation, we want to create the relation with the distance. So we are now considering here the power density. So that means how much power is delivered from that antenna at a distance R. So for that point of view, then power transmitted, that is PT, then the power density at a distance R from the radar is equal to the transmitter power divided by the surface area of the sphere. Okay, so that means what? Simply we can write it like this: the power density, this one. Let's say what we are doing, we are now discussing this power density. Let's say, so this power density is given by PT divided by 4 pi R square. So simply that is the power density at a distance R from this antenna. Okay, now so this is the value PT upon 4 pi R square watts per meter square. Then now, so again this will be the value. I am using the same, but what I have discussed in previous slide. So just reference I am just mentioning again here, PT upon 4 pi R square. So radar, basically this is a symbol of an antenna, power density we will discuss. But if radar will employ what? The directive antenna, that means this is a case we have just simply for consideration, we are considering an isotropic source, but actually when the radar system we will deploy it, so in that the antenna that we are using, that will be the directive. Directive means what? That have some signal will be transmitted in some specific direction. So this radar employs a directive antenna to direct the transmitted power PT into some specific direction, and also that means if we are sending the power in some specific direction, so that means it have the more power, that means we have to taken into the consideration its gain. Okay, so gain we have to taken into the consideration, that is denoted by the factor G. This is also very important factor regarding the antenna terminology. Okay, that we have discussed already. We have discussed these parameters in the subject antenna and wave propagation. So after that, now we will take into the consideration the density part. So the power density will get changed. So it is simple power density multiplied with this factor gain G, and it will show the directive power right now. So the power density will become again PT into G upon 4 pi R square watts per meter square. Okay, now let's say this power is now moving towards the some specific direction at a distance r. So what will happen? The target which is available at few distance r from this section transmitted antenna, that will intercept a portion of power. Okay, this is the main concept behind this radar working principle. Radiate it into the various directions. Okay, now that object will observe the power, and again it will come on to this portion. Let's say it is a target transmitted signal from here, let's say this portion, and moving towards the radar target, and target will absorb the power and re-radiate it back to different sections. So a measure of this amount, this power which have been reflected back by the interception of the target. So a measure of this amount of this incident power intercepted by target and re-radiated back in the direction of radar, which is denoted by radar cross section of target, which is simply denoted by the factor or the symbol, by the symbol sigma. Okay, that means what? Some power will be coming here, let's say PT, it will absorb and it is re-radiated back into some direction like this. So here it will absorb this antenna will absorb the receiving antenna will receive this radiated power. Okay, this will give the information regarding the presence of any object, and this portion by which this power is radiated back, it will known as the simple radar cross section of the target. So that means the total power that is intercepted by a target having an area, means let's say if any huge sizes will be this, and some specific part it is power will now striking, and only that portion will absorb this power, because we are considering the directive antenna, because they have this like type of pattern like this. So it will not consider cover up to the whole portion, but a specific part it can cover. So at some from all the part, some specific part we are consideration, and the absorption this power we are now calculating. So at this end, from this antenna it will absorb some power by this target G. So what will be the value of this power intercepted by the targets, which is simply the power density multiplied with the area by which it is now interacting. Okay, so this will given by PT into G upon PT into G into sigma upon 4 pi R square watt. So sigma has the characteristics of a particular target and measure of its shape and size. Now we will discuss next, because in the consideration in this reflected power we have the consideration the target or regarding the object which we have to detect. So we will study this parameter sigma now. Okay, so again, now power density at the radar station will be what? The same power which is going back to this direction, PT upon 4 pi PT into G upon 4 pi R square, and it is reflected back towards the receiver, okay, or the transmitter section again at radar section. So same the distance it will also cover. So this power density of echo signals, which is generally named as this reflected signal, generally named as an echo signal, so which will give the presence of some target. So it will given by PT into G into sigma upon 4 pi R square into 1 upon 4 pi r square. So simply the power will be given by Pt into G into sigma upon 4 pi r square whole square watt. So this is the simple power that can be intercepted by a target and re-radiated back towards the which is received at the receiver station. So the radar antenna captures a portion of this echo power. Generally this is the echo power, and consider the effective area of receiving antenna. Okay, so that means this power is coming back and it is collected by the receiver section. But receiver section antenna having, it will have the characteristic, another characteristics of antenna, that is the effective aperture, that will signify to the user that the how much area of the actual size, from the actual size of receiving antenna, how much area of that antenna is collecting the power, which is simply the concept of this effective area. So let's say we will denoting it by AE. So the power received by the radar is given by, let's say, PR. We are giving here by the factor PR, and PR, its value will be PT into this reflected power multiplied with this effective aperture AE. So PT into G into sigma into AE upon 4 pi r square whole square. So this will be the now radiated received power at the receiver section from the target. So we will now study this. After that, this power we are now receiving at the receiver section. Now what next? This we are getting the power value. After that, now we have to discuss the radar range. That means distance r we will relate. So for that point of view, we are considering the another point, another important factor, parameter, that is maximum radar range, that we are considering. Means at the maximum distance at which the receiver station will detect the target, it is denoted by parameter r max. So this is the distance, it is simply defined as this is the distance beyond which the target cannot be detected, and it occurs when the received echo signal power just equal the minimum detectable signal. This now another important thing that comes here for maximum radar range equation means what? The minimum power that can be detected for a maximum distance, the minimum power at the receiver station, the receiver antenna is capable to detect and give the response regarding this minimum power, which is named as a minimum power signal. That means minimum detectable signal. Means if some power it is detecting, that means what? It is able to detect the signal for corresponding strength, minimum strength signal. So it is denoted by S minimum, let's say. So this, for this specific value, minimum signal strength, the R will be R maximum, beyond which it cannot able to detect the target, because the power is not absorbed by the or not collected by the receiver section. So when PR is equal to S min. Okay, so this PR is equal to, when PR is equal to S min, and at this condition R will become R max. So this is the condition for maximum radar or the minimum power detection. So substitute this value in this equation that we have derived. So in substitute this value, so we will get the answer PR is equal to that we have used, PR is equal to PT G into AE by 4 pi r square R max. So this PR you can also use it as an S min for this value of R. R will R max when, so PR will become S minimum. So radar R max value, as you can see here, it will equal to PT into G into sigma into AE upon 4 pi square S minimum raised to power 1 by 4. So this is the maximum radar range equation. This is the value of this equation, will gives the information regarding the maximum radar range equation. So meant for minimum power, we are able to detect at the receiver station, and corresponding R will named as a maximum radar range. Okay, so this now for this maximum radar equation, now we can change it because we have already considered that the transmitting antenna having the gain G. We have now for the directive, and also we know the relation of G gain is equal to 4 pi into A by lambda square, that we have already studied. So now we are considering this point. So, and when we will put into the previous equation, this one, when we put this value G is equal to 4 pi into A by lambda square. So when we will put into the previous equation, so this value of this R max will become Pt into 4 pi into Ae upon lambda square into sigma into Ae upon 4 pi square S min raised to power 1 by 4. So after simplification, so this R max will become in terms of effective area Pt into A square into sigma upon 4 pi lambda square S min raised to power 1 by 4. Or we can also convert this in terms of, we write the equation, this previous equation in the form of simply gain G. So it will equal to R max is equal to Pt into G square into lambda square into sigma upon 4 pi cube S minimum raised to power 1 by 4. So this is the now another form of this maximum radar range equation. Now, before moving ahead or to discuss the another factors like on which this maximum power radar range equation will depend. So one important thing that we have to take it into the consideration, that means the transformation of this maximum equation from, let's say, from this equation A to equation B, means from G to AE. It is only possible, only the one assumption, if we will take it into the consideration. What is it? That means the gain what we are using in the derivation, that is the regarding the transmitting antenna gain, and that power which we are detecting at the receiver for this R max value at the receiver antenna. So receiver antenna and the transmitting antenna have the same parameters, like if it transmitting antenna have the gain, directivity, effective area, the same will have. But it is, we are now transforming the from equation A to equation B by considering that G is equal to 4 pi into A by lambda square. So it is only possible when we are now considering this, the transmitting antenna receiving antenna will be same. These should be same. Same we are using. Then this transformation from equation A to equation B is possible. Means these two transmitting and receiving antenna should be identical. So generally what we are doing in advance, that we are using the duplexers instead of this transmitting antenna, means we can use the antenna in the duplexer as a transmitting as well as a receiving antenna. So the this G will or the A should be same. So this is the one important thing that we have to take into the consideration. Now from the previous equation R max that we have already seen, it will depend upon the transmitted power Pt, frequency F, radar cross section sigma, and the minimum receiver signal PR min, let's say. So one by one we will discuss. So let's say first we are discussing the transmitted power Pt. So from the previous equation, from any one equation, we were finding that R max is equal to, or R max that is proportional to this Pt raised to power 1 by 4. Okay. Okay, so that means what? If we want to increase double the range R, so how it is possible? For that point of view, the power should be 16 times. When it will be the transmitted power, means the transmitted power will be high. So only this radar range equation can be doubled, means high power we have to use. So this is the dependency of this R max to this transmitted power. Next one, that is the frequency. Okay, so for frequency, as you can see that is R max proportional to this under root of f, or R max proportional to 1 by under root of lambda. Now that one is the one important thing that we have to take into the consideration. That means if we are increasing the frequency, so R max will also increase. When we are increasing frequency, means we just this is our obvious requirement, that we are able to detect the high as much as possible more distance. So for that point of view, from the previous equation we are deriving that f, we increase f and R max will also increase. But simultaneously f is dependent to the wavelength lambda. So that means if we are increasing this R max, we have to increase this frequency, and ultimately what we are doing, we are reducing the value of lambda, then R max will increase. Okay. Now one important thing that we have to take into the consideration, that but this lambda will also dependent on to the beam width of the antenna. So beam width of antenna, it is equal to beam width of antenna is proportional or equal to the lambda by d, where d is the diameter of, let's say for example we are considering the parabolic antenna, so this is the diameter. So what means that beam width proportional to this value of lambda. That means if lambda is decreasing, beam width will also increase. That let's say we are using this type of pattern, okay, this beam width. But if frequency will increase, this beam width will decrease. That means like this. So beam width. So for this is in a conflict here for this frequency. That means the beam width will reduce. So the target only receives some specific portion, not to the able to give the correct information regarding the shape and size of any target. So this is the one important thing that we have to take in. So frequency we can increase in a limited manner only. So that's why its beam width not much affected so high. Okay. Next one, radar cross section. So this R max also proportional to sigma raised to power 1 by 4, but sigma just to give the information regarding the shape and size of an antenna. A shape and size of target. But right now this is not a controllable factor of sigma is not a controllable factor for any radar section, because it will depend upon in the present scenario the war machines are very sleek. So that's why its actual size is not able to identify by the radar, and also the enemy the other countries are just creating their aircraft in such a very sleeky manner, very evade in such that, so painted and like that, so that can be ignored this, they can be hide from the radar range. Okay, so this is a very also another important thing, because so this sigma is not a controllable factor in our hand. It is this is the characteristics of radar section, but it is changing as per the requirement of this, what are the target is now present. Last one, that is the minimum received signal PR min. So the minimum detectable signal at the receiver PR min sets a limit on the receiver sensitivity, means to detect the minimum strength of signal. This is the simply our antenna characteristic at the radar section, receiver section. So that means it when our radar is much more effective when it will detect the minimum strength of signal. So that means its minimum detectable signal strength PR means set the limit of receiver sensitivity. That means the noise figure, ultimately what we are considering, the noise figure of the receiver is a factor that is to be controlled for obtaining this R max, because for this point of view we are considering the value of this minimum noise power also. So for that point of view we are, let's say, noise figure. So for that we are just drawing two figure. For two figure that I am now considering here, that is the let's say signal we are transmitting SI, corresponding output is our, let's say, S naught for this receiver section with gain G, and also let's say we are considering for input power Ni, we are considering the output power N naught for the radar receiver with gain G, and also considering the equivalent noise power, okay, generated into the receiver. That is another factor. So if we will discuss this noise figure, that is the S by N ratio at the input to the S by N ratio at the output. So that means what? Si upon Ni, that is divided by S naught by S naught. Okay. So when we will arrange this, so we can write this equation like Si upon S naught or into N naught upon Ni. We can write it like this one. So from these two figure, this value of S naught is what? G into Si, and N naught is what? G into Ni plus del N. Okay. So we will put these values in the noise figure. So when we will put this value, so F will become it will become Si upon S naught. So Si upon G into Si. Okay. Next that is N naught over Ni. So N naught value we can put G into Ni plus del N upon Ni. So we can from this equation we can derive this equation value F is equal to 1 plus del N upon G Ni. So or we can write it this del N is equal to F minus 1 into G Ni, and we are transmitting this will be the value of this equivalent noise, this is which is generated into the receiver section, and the value of this Ni, the receiver input noise, that is equal to what? K T naught B. T is T naught temperature, B beam width, bandwidth, and K is the Boltzmann constant. So this will del N will become F minus 1 into G into K T naught B, let's say. So what will happen to detect this signal? This will be the equivalent noise which is generated into the receiver, and some power is now also coming. So what is our now main impact here? That we have to detect the minimum signal strength, and this some power is also coming. Let's say we are considering this PR minimum that is detected by the radar, and this del N is also introduced into the receiver section. So to detect this target, if this PR min is less than this value del N equivalent noise, then radar is not able to detect the target. So to detect the target for a minimum detectable signal, this PR min value equal or greater than this value of equivalent noise which is generated into the receiver. So in this condition only, if this PR min equal to with this radar equivalent noise power, then the radar can detect the signal. Okay. So in this way, so this will set limits onto the receiver sensitivity of a receiver section. So in this way, R max will become, we can now write it in like into the PT into AE square into sigma upon 4 pi lambda square into F minus 1 and K T naught B into g raised to power 1 by 4. So this will be the value of this R max in case of this minimum received signal PR min. Okay, so this value we have to, another important thing that we have to taken into the consideration. So this value, again our range equation for the regarding PR min is now changed for by taking into the consideration equivalent noise. So this is the now from my side regarding the topic radar range equation and its impacting factors. Thank you and Jai Hind.